So let us start first law of thermodynamics. See, this is the time which we are waiting for. Okay, first law of thermodynamics. It's one of the very interesting, like from now until I complete thermodynamics. Okay, so except maybe you will feel some kind of lagness in the last topic, thermodynamic relations, because thermodynamic relation is full of formulas and like what I could say, derivations. But until that, from now until that, each and every topic is going to be very interesting. That is thermodynamics, and you will start to feel thermodynamics. Okay, already I guess you would have started when I started work. Okay, you already started to feel thermodynamics when I started work. And heat. Now first law. See, first law of thermodynamics is divided, or we can say that it can be written in different forms. For closed system, we have first law of thermodynamics. For a cycle, okay, only for a cycle, thermodynamic cycle, we have one form of one form of first law of thermodynamics. For open system, steady state, unsteady state, for both we have separate first law of thermodynamics. But ultimately, whatever may be the form, either it is for a closed system, or it is for a cycle, or it is for a open system, that is a steady state or unsteady state, whatever may be, the nature or what that first law of thermodynamics is saying. First law of thermodynamics is going to say conservation of energy. It is stating conservation of energy. What does it mean by that? Energy can never be created, neither be created nor be destroyed. It can be transferred from one place to another, or one point to another. It cannot be created or it cannot be destroyed. That is what this first law is going to say in all the forms. There are n number of forms. We will be discussing one by one. Okay, in all the forms, the basic nature will be conservation of energy. Energy will neither be created nor will be destroyed. It's going to be transferred from one place to another place. And we will start with first law of thermodynamics for a cycle. Okay, so this is our first form of first law of thermodynamics. Next we will go for process. Okay, in that also we are going to discuss for a closed system. A closed system, process. Then we will go for open system. In that we will discuss steady, then unsteady. These are the different forms. Okay, so this is for a cycle, thermodynamic cycle. And what does this says? What does it states? First let me explain you, then I will be giving you examples. First law of thermodynamics for a cycle, it states that the total work done, or in other words, net work done in a cycle will be always equal to total heat transfer. It's nothing but it will be always equal to net heat transfer. Both are same only, I'm just writing it in a different form. Summation of work will be equal to summation of heat. Similarly, net work done is equal to net heat transfer. This is valid. Okay, so this both are same. Okay, both this statement is valid for a cycle only, and there is no other assumptions other than that of this. Okay, what is that? It can be applicable for both reversible and irreversible cycle. So no restrictions, no restriction, no restriction. Note down all the assumptions properly. So this particular equation for a cycle, it has no restriction, which means I can apply for both reversible and irreversible cycle. Okay, both reversible and irreversible thermodynamic cycle. Okay, right. Now what does this statement states? Okay, fine, this is the first law of thermodynamics for a cycle. What it is actually saying, let me give you one example. Okay, just we will take some PV diagram. Okay, and I'm defining you some cycle. Okay, So let this be a process 1 to 2, let this be another process 2 to 3, let this be another process 3 to 4, and let this be another process 4 to 1. During process 1 to 2, okay, I am just giving you some random process, okay, that's just for an example, just for explaining you this statement. Okay, what is mean by net work, or what is mean by summation of W, what is mean by summation of Q, or what is mean by net Q, what it states. For example, during process 1 to 2, there was some amount of heat which is supplied to the system. Okay, I am supplying it to the system. Okay, and during process 2 to 3, let us assume that there was some work which is done by the system. System is doing some work. All are some, I am just giving you some example. Okay, so later we will study about this cycle in detail. Okay, all the types of cycle, Rankine cycle, Brayton cycle, and gas absorption cycle, gas refrigeration cycle, everything we will be studying in detail in applied thermodynamics. That is a separate subject. But for understanding that subject, you need to know a strong base in thermodynamics, in basic thermodynamics. Okay, so during 1 to 2 process, heat is supplied. Let us assume during 2 to 3, work is done by the system. Okay, and during 3 to 4 process, let us assume heat is rejected. Okay, during 4 to 1 process, let us assume that I am doing some work on the system. Okay, I am doing some work on the system. Okay, and in 1 to 2, there was no work transfer. Similarly, in 3, 4, there is no, I am just assuming it. Okay, I am just assuming it. Okay, and in 2, 3, there is no heat transfer. In 4, 1, there is no heat transfer. So during this process and this process, 1 to 2 and 3 to 4, no work transfer. During 2 to 3 and 4 to 1, no heat transfer. That is my assumption. Now how to apply this law here? What does this law says? Summation of W is equal to summation of Q. What actually it means? The net heat transfer, or the total energy, okay, the total heat transfer, that is also a form of energy, right? The total heat transfer, that will be equal to total work transfer. Again, it is simply an energy conservation equation. Whatever the energy, okay, whatever the total heat transfer, that should be equal to work transfer. They are just giving you the conservation of energy only. Okay, now, so if you observe it, first how to find out this net work transfer? The summation of W, which is going to be equal to W net, which will be equal to how much? What is going to be? Nothing but I just need to add these two. Okay, that's it. This is a cycle, this is a thermodynamic cycle, so just add this two. Okay, so W 2 3, it will be positive because work is done by the system. 4 1, work is done on the system, so let me take it as negative. Okay, minus W14. So sign conventions are very important. So whenever you are finding summations or a net value, the sign convention is very important. What are the sign convention we discussed already? Work done by the system will be positive, work done on the system will be negative. Heat transfer, heat supplied to the system will be positive, heat rejected will be negative. Okay, so now summation of Q is equal to Q net, that's going to be equal to here Q12 is supplied to the system, so plus Q12, Q34 is rejected, so minus 34. So what does first law of thermodynamics of a cycle states? Summation of W and summation of Q, that is net work and net heat, are same, which means W23 minus W14 will be equal to Q12 minus Q34. Okay, so this is what. Okay, I am just giving you an example. See, in problems what they will do, they will be giving you the numbers. Okay, something like what is Q, some 20 kilojoule, 30 kilojoule, 40 kilojoule, 50 kilojoule, like that they will be giving you the number. You can substitute here, you can find the unknowns. Okay, some 3 values will be there, for example, 1 will be not there. Okay, so now let us understand what are all the consequences of this first law of thermodynamics. See, I given you the statement of first law of thermodynamics for a cycle only. From that we are going to have different consequences. Totally 4 consequences are there. Okay, so we will start one by one. What is the first consequence? I didn't written anything, right? So I will be writing you the consequence after explaining you, or you itself will understand before I am writing it. Okay, I will make you to understand that. Listen, if let us consider State 1 is there, state 2 is there. I am doing some process from 1 to 2 along a path A, okay, along a path A, and another process from 2 to 1 along a path B, okay. So A to 1 to 2 along a path A and 2 to 1 along a path B. So this constitute a cycle, right? So 1 through A, 2 through B, 1, it is cycle. Okay, now our first cycle which I considered. Okay, what is the next cycle? Listen. Initially again from state 1 to state 2 along a path A, then from state 2 to state 1 along a path C. Okay, along path C. Okay, so 1 A 2 C 1. This is cycle 2. I am considering another cycle 2. Now the question is, okay, now what I am going to do, the analysis is very simple. I am going to apply first law of thermodynamics for this cycle. First let me apply for the cycle 1. Okay, if I apply for cycle 1, let us assume that let us assume, I will take in general case that everywhere heat transfer and work transfer is happening. We are not going to restrict anything. Okay, so for example, when the process A is happening and the process is happening through path A, okay, the total heat transfer, okay, the heat transfer here will be, let me take it in our general sign convention d dash, or you can take it as delta, okay, whatever, delta Q or d dash Q, it's up to you. Okay, that is heat transfer which is happening during the process, or else you can simply take like this also. Okay, let me take like that, heat transfer along a path A, okay, during a process 1 to 2 along a path A, okay. Now, and heat transfer along this path, okay, that I will take it as Q 2B1, okay, Q2B1. See, here we are not worried about sign convention, whether it is positive or negative. If the heat is getting rejected, automatically it will become negative. If heat is getting supplied, automatically it will become positive. We are not going to worry about that, okay, because we are just doing some analysis. Okay, now that will be equal to what? Summation of heat transfer in this cycle will be equal to summation of work transfer, right? So work transfer during this process 1 to 2, okay, that will be W1 A2 plus similarly work transfer in this process 2 to 1, okay, let that be W2B1. Okay, so that is for cycle 1, okay, that is for first cycle. Now for cycle 2, 1 to 2, again heat transfer is going to be 1A2 plus 2 to 1. So but now the path was C, okay, now the path is changed similarly, which is equal to W1A2, that is same path only, okay, same path only, and 2 to 1 is through path C, okay, so W2C1. Now let me subtract this 2. Again, I am not worrying about sign convention, okay. So if the sign convention varies, based on that it will vary. If it is heat supplied, positive, heat rejected, negative, work done by the system, positive, work done on the system, negative, right. So let me subtract this 2. So the second equation is for cycle 2, first equation is for cycle 1. So if I subtract it, what will happen? These two are same, right? That first heat transfer 1A2, heat transfer 1A2, same. Work transfer 1A2, work transfer 1A2, same. So Q2B1 minus Q2C1, okay. Just I am subtracting this 2, that will be equal to here W2B1 minus W2C1, okay. So this is our equation which I got, right? Now when I am discussing about work transfer, we know very clearly work transfer is a path function, which means, see, listen carefully. If I do a process from 2 to 1 through path B, okay, and if I do a process through 2 to 1 through path C, work transfer in this path and work transfer in this path is not going to be same, because they are path function. As I'm changing the path, from B to C, okay, as I'm changing the path from B to C, work transfer in this path, that is the red color path, will not be equal to work transfer in this path, that is black color path. That is the conclusion which we got earlier in work transfer. Okay, so W2B1 is not going to be equal to W2C1. This is well known fact. If they are not same, okay, there is this path and this path, the work transfer is not same, I can write something like this, right? W2B1 minus, I will bring this left hand side, W2C1 is not equal to 0. Okay, I can write like that, right? I can write like that, which indicates this term is not equal to 0. This is what we got by subtracting this 2. That term is not equal to 0, which clearly states Q2B1 minus Q2C1 is not equal to 0. Right hand side is not equal to 0, then left hand side will also be not equal to 0. So finally, we are getting Q2B1 is not equal to, I am bringing this to right hand side, is not equal to Q2C1. This is it. By using that particular equation, by using this particular equation, what we can conclude, right? I hope you would have already got it, right? So there is nothing but not only work transfer, heat transfer is also a path function. Why? I am doing process from 2 to 1 only, but if I do through path B, I am getting this heat transfer. If I do through path C, I am getting this heat transfer, and they are not same, and both of them are not same because we just derived it. They are not same, which means if I change the path, even though starting state and ending state are same, but if I change the path, the value of heat transfer is varying. So clearly from this equation I can conclude our first consequence of first law of thermodynamics: heat transfer is a path function. Okay, this is the first consequence. We already know work transfer is path function, and we discussed it earlier. See, since heat transfer is becoming path function, there are many other things to be included in that. What are all those things? We already know that. We already studied that in work transfer. Okay, so now we will understand it by comparing work transfer and heat transfer. That is, what are all the common things between those two. So the first consequence of first law of thermodynamics is heat transfer is a path function. By using this single consequence, we can get to know about many common points, okay, or common things between heat transfer and work transfer. We will learn that one by one. Okay, still we are in first consequence only. Okay, so in that first consequence, by observing that first consequence, we are going to get few more points which is going to relate heat transfer and work transfer. What are all those? First point, both are path functions. As we proved both. Okay, work transfer is a path function which has been proved earlier, and just before I just proved that heat transfer is also a path function. Okay, now what is the second statement? See, if it is a path function, okay, so some process is happening from 1 to 2, okay, another process is happening from 1 to 2, let it be some path A, some path B, okay, some 1 to 2. If it happens in this particular path, I will get different heat transfer. If it happens in this particular path, I will get different heat transfer. Similarly for work transfer also, okay, they will vary based on the path. So if they are varying based on the path, they are independent of the state. They are independent of the state, or they are independent of the point. So both are not state function, okay, or else other word for that is both are not point function. Both heat transfer and work transfer are not state function or not point function. If they are not state function, if they are not point function, what I can conclude? We discussed that earlier already in a detailed manner. If they are not point function, if they are not state function, we can conclude that they are not properties also, because properties are point function. They will vary based on the point, they will vary based on the state. Okay, so both are not properties. Okay, so both heat transfer and work transfer, here both implies heat transfer and work transfer. Okay, so both are not properties also. Okay, now fourth point. What is the fourth point? If they are not properties, then what I can say about its differential? If they are property, then they are exact differential. If they are not properties, they are inexact differentials. Okay, they are inexact differentials. Right, we know this already. What is exact, inexact, I explained in the previous videos. Okay, now finally, this is also I already explained, but still we need to learn it here. Both are energies in transit. What does it mean by that? We have two types of energies. Okay, one is energies in transit, another one is stored form of energy. This is also dynamic. Okay, so we can say that this is dynamic, that is static. Okay, stored form of energy is static. Regarding stored form of energy, we will discuss in detail when we are reaching the second consequence. Okay, now in the first consequence, what is this energies in transit? Energies in transit means when the process happening, okay, when the process happening from 1 to 2, during that time only this both, okay, both heat and work will have its meaning. Both heat and work will have its meaning only when process is happening. During the first state or during the second state, it has no meaning at all. It has no meaning at all. You can just imagine that. Take a container. Okay, so if it has some gas at some particular state 1, do you say any work done for this particular state? We cannot say that. When can I say about work done, or when can I say about heat transfer? When some process is happening. Okay, when something is transferring, that time only I can say about that. Okay. Now, actually, before this fifth point, I should have given one more point. I forgot that, in fact. Okay, let me give it here. Okay, let me change this to 4, and let me change this is to 5, and let this be 6. What is the third point? It's a boundary phenomena. Okay, I forgot to. Both are boundary phenomena. So what does mean by boundary phenomena? That is, both heat transfer and work transfer should cross the boundaries. Okay, so if I take a system like this, okay, if I take a system like this, both heat transfer and work transfer should interact with its surrounding. Okay, there should be interaction of heat transfer with surrounding. System and surrounding should get interacted. So heat should cross the boundary. It should cross the boundary and it should come out of system and it should interact with surrounding, or from the surrounding heat should come and interact with system. Similarly, work should be interacted with the surrounding, or surrounding should interact some amount of, like either work is done by the system or work is done on the system. Okay, so work is done by the system means what? System is doing some work on the surrounding. For example, take a piston cylinder arrangement. This is my system. Okay, now if I'm supplying some heat, okay, what I'm doing, from surrounding I'm supplying heat to the system, so it is crossing the boundary. Okay, there was an interaction between surrounding and system. Similarly, when I'm supplying heat, this piston start moving up. What actually it is doing? It is pushing this air upward. Air is surrounding, right? Air is our surrounding, and this piston is pushing that surrounding upward, which means it is doing some work on surrounding. So work is done by the system on the surrounding. Heat is transferred from the surrounding to the system. So there should be interaction between system and surrounding, either if it is a work or if it is a heat. Okay, that is what boundary phenomena. I should have said it before itself, before coming for the last point. Okay, so which means both heat transfer and work transfer should cross the boundaries. Okay. Okay, that means there should be an interaction between system and surrounding. Okay, here either it is rejecting from surrounding, or it is accepting, like the system is rejecting to surrounding, or the surrounding is supplying heat to system, whatever it is, there should be, okay, the crossing of boundary should be there. Now finally, sixth point, both are energies in transit. What does it mean? As I was saying already before, transit means when the process is happening. When the process is happening, that time only this energies will have meaning, which means both heat transfer and work transfer. When it is at a state 1 or it is at a state 2, it doesn't have any meaning. Okay, and that is why most of the times we will use work transfer, okay, this transfer, and heat transfer. So the correct way of using the word work and heat, okay, is work transfer and heat transfer. Like generally, if I am using it as heat and work, it is actually wrong. Okay, like day to day, like we can use it in general, but the correct way of representing, or the correct way of using the word is work transfer and heat transfer, because both of them are energies in transit. Okay, when the process is happening, that time only it has meaning. Okay. Right, so that's it. And I forgot to mention you if it is inexact differential, yeah, I should have mentioned it. If it is inexact differential, how I need to mention it? Delta Q or D dash Q, right? Delta Q or D dash Q. And similarly for work transfer, it's going to be delta W or D dash W. We should not mention it as dq, we should not mention it as dw. This is wrong, because they are stating exact differentials. Okay, so exact differential means it is indicating the change, small change, infinitesimally small change of q, infinitely small change of w. That is absurd, that is completely wrong. We can say that the change word is completely wrong with respect to q. Okay, I explained to you in the previous videos, okay, regarding work transfer that time itself. I cannot say that I'm changing some work. I can say that some small work is done. I can say that some small heat transfer has happened, but I cannot say that change. Okay, that is wrong. So this is wrong. Properties are only changes. We can mention it with change, and these work transfer and heat transfer both has to be mentioned like delta W, delta Q, D dash Q or D dash W. Okay. So now we will go for the second consequences.